Very good morning, children. In this video, we are going to see some topics that are really taken onto the PUC board, but still they are useful, so we are going to learn them. And whenever we are discussing about the change in heat, for example, the change in heat, if you take one bottle of water, yeah, we are having one bottle of water. If you are having this bottle of water, it is around 750 ml. Or if you take 1 liter of water, whatever quantity of water it may be, but what will you say? The boiling point of water is 100 degrees Celsius. Means the boiling point of water does not depend upon the amount of substance. The boiling point of water does not depend upon the amount of substance. So such kind of property which does not depend upon, means the boiling point does not depend upon the amount of substance, we call as intrinsic property. Means some properties are there that does not depend upon the amount of substance. Is it not? What is the meaning here? Means we are linking up to the heat capacity. You are going to heat the water and it will change from the liquid state to gas state. Means there is some change in the heat content. Is it not? Then only the water will boil. And similarly, we had learned in the chapter, like the 5th chapter, states of matter, which are already the related topics like surface tension, viscosity. These properties, for example, you can see the water and the honey, which will not flow very fast. Honey or water, honey will not flow very fast because these particles will be held very close to each other. It's called as the viscosity of the substance. Which does not flow easily, it will have more viscosity. So it does not depend upon the amount of matter. Those properties we call as the intrinsic property. In a short, the property of the substance which does not depend upon the amount of substance is called, or the amount of matter is called as intrinsic property. But the property which depends upon the amount of substance, the property which depends upon the amount of substance, they are called as the extrinsic property. What are they called as extrinsic property? These are two intrinsic and extrinsic property. Two properties that we are going to see. What are the one of the property we have learned? Extrinsic property. Property which depends upon the quantity of matter. A property which depends upon the quantity, which depends upon the quantity of matter. We are calling as the extrinsic property. For example, we know about mass, we know about volume, we know about internal energy, we know about the heat and free energy or the entropy. This all depends upon the quantity of matter. The quantity of matter. So when I depend upon the quantity of matter, we call as the extrinsic property. The properties like surface tension, viscosity, boiling point, freezing point, vapor pressure, pressure, or temperature, it does not depend upon the quantity of matter. So we call them as the intrinsic properties. Just to introduce them. So now, when you are heating a substance, it will take some amount of heat. It will take some amount of heat. For example, you had heated the substance with increase of temperature from 25 degrees Celsius to 26 degrees Celsius. Is it not? Okay. Now you are expressing the amount of heat that you are supplied in the form of degrees Celsius. Or you can express the same in the form of Kelvin. In the form of Kelvin. Is it not, children? Yes. So the amount of heat absorbed by a substance, the amount of heat absorbed by a substance to raise its temperature by 1 degree Celsius or 1 Kelvin, there is some measurement. There is some measurement. That measurement we are calling as the heat capacity. What are we calling it as the heat capacity? So what is meant by this heat capacity? Means amount of heat required to change the temperature of a substance by a given amount. amount of heat required to change the temperature of a substance for a given amount. We are calling this one as the heat capacity. Now, you may increase the temperature of the substance. For example, you are taking the substance 1000 grams or 1 kg. It doesn't bother. But here in chemistry, we will not take such quantities. Our chemical reactions we will consider for very less amount of substances. Hence, we are going to study, for example, 1 mole is the smallest amount that we know, which is very useful in all the chemical balancing equations. So, the amount of heat absorbed by 1 mole of a substance, 1 mole of a substance, the amount of heat absorbed by 1 mole of a substance to increase its temperature by 1 degree Celsius or 1 Kelvin. We are calling it as the molar heat capacity. Yes or no? Then get the definition here. Amount of heat required to raise the temperature of 1 mole of a substance by 1 degree Celsius or 1 Kelvin we are calling it as the molar heat capacity. What are we calling this as the molar heat capacity? It is generally represented with the symbol small c suffixed with small m. Here m stands for the molar heat capacity, small m we are using, small c. Molar heat capacity, small c suffixed with small m. It is also given as the ratio of heat capacity by number of moles of the substance. How is it given as the ratio of heat capacity? Heat capacity, we have already got the definition. This is generally represented with the capital C upon number of moles. Number of moles of the substance, we know how to represent small n. So we are giving the molar heat capacity is equal to specific heat capacity upon number of moles of the substance. But don't forget, the heat capacity is equal to the molar heat capacity and the multiplied with molar mass of the substance. Mass of the substance. Yes, small m stands for the mass of the substance. This is useful for the next points. I hope these definitions are very clear for you. Very simple definitions. These are all. Once again, you can rewind the video. But if you are calculating the amount of heat required to raise the temperature of a given amount of substance, the amount of heat required to raise the temperature for 1 degree Celsius or 1 Kelvin for a given amount of substance, and such point we will use the definition called specific heat capacity. What is the definition we are doing? Specific heat capacity. We are reading the definition here. The amount of heat required to raise the temperature of a unit mass of a substance, by 1 degree Celsius or 1 Kelvin. So we are calling this one as the specific heat capacity. We are calling this one as the specific heat capacity. Here the heat absorbed by substance we are giving in the form of specific heat, that's called C, small c, and here don't forget, molar heat capacity is given as small c suffixed with m. But what we are calling here specific heat is also represented with the small c only, but it is not suffixed with small m. Okay, children. So specific heat into mass of the substance into change in the temperature. So the heat absorbed by a substance, it is a product of specific heat. What is the meaning of specific heat? The change in the amount of heat required to raise the temperature of unit mass of a substance by 1 degree Celsius or 1 Kelvin is called as specific heat. So the heat absorbed by a substance, it is a product of specific heat into mass of the substance into change in the temperature. How is the specific heat given? Specific heat is given with the small c. Mass of the substance is given with the small m, and change in temperature delta T. But we know the specific heat into mass of the substance is given as the capital C. How is this one given as the capital C? So we are seeing the heat absorbed by a substance now, it is equal to capital C into delta T. Note down this because we are going to derive one equation from these values. We came to know the heat capacity is represented with capital C. How is the heat capacity represented, children? It is represented with the capital C. But this heat capacity, when you are studying at constant volume, now the heat absorbed, how we will give? It is also absorbed at the constant volume, It is now represented as, we had seen this equation. What equation we had seen? The heat absorbed is equal to the product of heat capacity into change in the temperature. Heat capacity into change in the temperature. This capital C is the heat capacity and delta T is the change in temperature. Right. Now we are being at constant volume. The heat absorbed is given as Q suffixed with V. How is it given as? Heat capacity and constant volume, the product of change in temperature. But here this change in heat absorbed at constant volume, which is the product of heat capacity at constant volume into change in temperature, is nothing but change in internal energy. Delta U is equal to change in internal energy. Delta U is equal to change in internal energy. Whereas the heat absorbed at constant pressure. Whenever the word constant pressure comes to you, you must not forget it is equal to the change in enthalpy. So the heat absorbed at constant pressure, how we give heat absorbed is equal to QP is equal to heat capacity at constant pressure into change in the temperature. Whenever we have a pressure constant, that is equal to change in enthalpy. Or these are given as the change in enthalpy. So now we are bringing one relation that we had already learned. The change in enthalpy for 1 mole of gas. Already 1 mole I mentioned. Means we are not bothering about delta Ng here. Delta Ng into R into T. Whenever 1 mole is given, already this is becoming 1. So we can say there is nothing but this equation is given as the delta R into T. Already N is 1. So we can say delta R into T. So for 1 mole of substance, the change in enthalpy, how we had given in the last class, delta H is equal to delta U plus delta R into T, because N becomes 1 for 1 mole of substance. Now we know delta H, how we are given the equation? Cp into Cp into delta T. What is the delta U value change in internal energy? Cv into delta T. Substituting those values in the form of delta H and delta V, that is equal to delta R into T So we are having the R constant, which is already 0.314 joule Kelvin inverse mole inverse, but delta T, there will be change in the temperature. So when you make all these as constant, delta T and delta T, you can now write the equation as Cp minus Cv into R, which is equal Cp minus Cv is equal to R. In a simple step by drop, or you can write like Cp is equal to Cv plus R, and we can rearrange the equation, but you can learn this as Cp minus Cv is equal to R. So this is a relation between, heat capacity at constant pressure and constant volume. Heat capacity at the constant pressure and the constant volume. Right on, children? Let's say here, children, a very important next level of the concept. We are having the word enthalpy. Regarding this enthalpy, there are many definitions to study. These all definitions are brought under a title called enthalpy change of a reaction. Enthalpy change of a reaction. We have learned change in enthalpy is given with the symbol delta H. Is it not? Change in enthalpy of the reaction is change in enthalpy of the given as the delta H. Change in enthalpy is generally given as the delta H. But in a particular reaction, if you want to study the change in enthalpy, you are going to study the known as the change in enthalpy of that reaction. How we are going to study the change in enthalpy of that reaction. For example, we are having one reaction. We know this reaction from many days. Methane on combustion, it gives carbon dioxide and the water vapor. So methane CH4, that is in the gaseous state, combined with 2 moles of oxygen gas to give carbon dioxide gas and 2 moles of water, that is in the liquid state. Now, in this, the reactants, what are the reactants? Methane and oxygen are the reactants. When these are in a balanced state, we know about the law of mass action. The mass of the products formed will be equal to the mass of the reactants involved in the reactants. So, in a balanced reaction, when all the reactants are converted into products, when all the reactants are converted into products, it is going to be studied as the enthalpy of that reaction. How is it going to be studied as the enthalpy of that reaction? What we are reading the definition now once again. The change in enthalpy. The change in enthalpy. How is the change in enthalpy given as? The change in enthalpy generally given as the delta H. When all the moles of the reactants as indicated in the balanced equation, when all the moles of the reactants as indicated in the balanced reaction have completely reacted to form products, completely reacted to form products, it is called as the enthalpy of that reaction. But the change in enthalpy of this is equal to the enthalpy of the products formed, total enthalpy of the products formed minus total enthalpy of the reactants participate, whether they may be gaseous state or in the liquid state. Whether they may be in the gaseous state or the liquid state. So how is the change in enthalpy given? It is taken as total enthalpy of the products formed minus total enthalpy of the reactants. In this reaction, what are the products then? Products are carbon dioxide gas and 2 moles of water molecule, that is in the liquid state. How to calculate the change in enthalpy for this reaction? Total enthalpy of the products. What are the products? Products are carbon dioxide. So the enthalpy of the carbon dioxide and enthalpy, where is this one? 2 moles of enthalpy, which is the enthalpy of water. How many moles of water had formed? 2 moles of water had formed. 2 moles of water had formed. So you multiply the coefficient to the enthalpy, and the water is mentioned in the subscript. Here carbon dioxide we can mention in the subscript. It is not necessary to place them in the bracket, but to understand enthalpy of the carbon dioxide plus enthalpy of the number of moles of the water formed products minus total enthalpy of reactants, enthalpy of methane. This is the H. Enthalpy stands for enthalpy of the methane plus how many moles of oxygen are involved? 2 moles are involved. So 2 moles enthalpy of the oxygen. Enthalpy of the oxygen. By this we can calculate the change in enthalpy of a particular reaction. Once we rewind the video. Now we are seeing standard enthalpy of a reaction. What are we seeing? Standard enthalpy of a reaction. For example, how does the hydrogen exist? Everyone knows hydrogen exists in the gaseous state, H2. It is its standard state. How is the nitrogen exist? The nitrogen exists as the nitrogen gas. It is its standard state. How is the carbon exist? It exists in carbon dioxide, you will say, or we may say it exists in the carbon monoxide state. But its standard state is carbon. Simply we will say it is in solid state. So these are the standard states. So when we are representing a particular reactant or product in its native form, it is called as the standard enthalpy of the reaction. It is called as the standard enthalpy of the reaction. Generally, the conditions what we measure is, we will measure the standard condition at 1 baric pressure and 298 Kelvin. When we will say it is at standard state when the substance is at 1 baric pressure and 298 Kelvin, we say it is at the standard state. So let's go with the definition once. Enthalpy change of a reaction. Enthalpy change of a reaction when all the participating substances are in their standard states. When all the participating substances are in their standard states, we call it as the standard enthalpy of a reaction. See, the standard state of a substance is derived at a specific temperature when it is in its purest form. When the substance is in the purest form and 1 bar pressure, generally at 298 Kelvin. It's called as standard enthalpy of a reaction. Means we are taking the reactants or products in their standard state. Products we will not consider. First we must consider the reactants are there in the standard state. We will be continuing this in the next lecture number 6. Note down these points.